Okay, class. This video will be recorded to explain an example on the Truss analysis using the stiffness method. In this example, we will use these matrices, which is K prime, member local stiffness matrix, the displacement transformation matrix, T, and the member global stiffness matrix. I have explained on this the establishment of these matrices in my previous class, and today I will focus explain a full example using these matrices, okay, in solving the displacement and also support reaction and axial forces in truss, okay, for this example. Okay, so in this example, we are going to determine the structural stiffness matrix. If you have been asked to determine the structural stiffness matrix, you need to provide the full elements of this matrix. And in this problem, we also need to determine the axial forces in the truss, given the AE is constant. Here we have a truss, okay, which is supported pinned, okay, at two of the joints. Okay, so now you can first give a knot, okay, to the elements, to the structure. For example, you can put the knots at the joints. Okay, so now in this truss we have 3 joints, therefore we can put the knots at each of the joint. Okay. Then we need to identify or give a naming for the elements. So in between the knots we have element number 1, and you need to draw an arrow, okay, to indicate the near end and far end of this element. Okay, and we have element 2, okay, joining knot 1 to 3, and with this arrow to indicate the near end and far end. Okay, so next we will need to draw the DOF. Okay, so you need to remember that in truss there are 2 DOF per knot. Okay, the DOF will be in the translation. Okay, so horizontal and also vertical. Okay, therefore you need to put this DOF, okay, at each of the knot. Okay, here the total DOF in this structure is 6 because there are 6 DOF. Okay, and there are 3 knots. Okay, so now we need to number the DOF. Numbering of the DOF can follow this guideline. We name the unknown DOF first, then the non-displacement or non-DOF. Okay, so you need to know that the DOF that associate with the support will be constrained. Okay, means that the displacement at the constraint direction will be equal to 0. Okay, so we can see that here we have the support, pin support, and at node 2 we also have this pin support. Therefore you can see that the DOF that associate with this support reaction, like for example the one that I put star. Okay, these DOFs are known. Okay, we know the displacement value which is equal to 0. Okay, if I put it here, D3, D4, D5, D6, okay, they are all known. Okay, we will name them later. That is why this DOF, the one that I circle here, okay, 1 and 2, okay, will be named first. Okay, so because they are all unknown. Okay, D1 and D2. So once you have identified the known and unknown displacement, you can determine the vectors of D and Q. Okay, D is the displacement, and the Q will be in the load or the force. Okay, vector. Okay, so now this Q will be also associated with the support reaction. So we are talking this at node. So I put it here nodal. Okay. So if there is a UDL on top of your truss structure, you need to transfer this UDL into the joint. Remember, our assumption in the truss analysis is we assume that all the loads are acting on the joints. Okay, so now we have known that D1 and D2 is D unknown. Okay, and D3 to D6 is equal to 0. Therefore, we can fill the vector for the D here. If you can see that D1 and D2 are unknown. Okay, then D3 to D6, we know the value and they are all 0. Okay, so they might have a value in a case like there is a support displacement. Okay, but not in this case. Okay, then we can determine the vector of the Q. Okay, so how to do that? Okay, you can make a partition. Okay, to just checking. Okay, because we will always know that if you have a D unknown, okay, the opposite side at the bottom, there will be the Q unknown. And D known at the bottom of the D vector, okay, will reflect that at the top of the Q vector, this is Q known. Okay, so then for the Q, I will advise you to start filling in the support reaction first. Okay, so you know that 3, 4, 5, 6 are associated with the support reactions. So you can name it accordingly, Q3, 4, 5, 6. And they are all unknown and need to be determined, okay, if request. Okay, and for Q1 and Q2, we'll be having a look on this location. Okay, so you will find that in this case we have 2 kilonewton acting at this joint, okay, at the number 2 direction. So therefore Q2 will have a value, and it is negative because it is acting downward. Why? This direction, the DOF that we drawn at each of the nodes, these directions are the positive sign. Okay, we are going to base on this direction. Okay, so if the loads acting oppositely, so there is we give a negative sign. So then we can start to determine the, I would say this is a global, member global stiffness matrix. Okay, so this will be in this form. Okay, please refer to the appendix. Okay, which template to be used. Okay, for member global stiffness matrix again. Okay, we need to determine. Okay, for all the elements. Okay, so this page will show on K1 for element number 1. Okay, so what you need to be filled in this template is Cx, Cy. You need to determine Cx, Cy. Okay, Cx squared, Cx, Cy, and also Cy squared. Okay, so how to determine the Cx? Okay, Cx you can use formula of cos theta. Okay, or x at the far end minus x as the near end divided by the length. Okay, so here I will show you how to use the formulas using the coordinate. Okay, so therefore you need to determine the coordinate for this node first. Okay, Cx and Cy also term as the directional cosine. Okay, so now we will have to put in the coordinate. You can put a reference at any of the joints you like. For example, I'm going to put my reference here, 0, 0. Therefore, for node number 2, this is node number 2, node number 3, okay, node number 1. So node number 2 will be 3 and 0. Okay, I'm talking about x and y, okay, coordinate. And number 3, we will have 3 and 4. Okay, so to determine the Cx, it will become, okay, you need to know which node is the far end and which node will be the near end. Okay, so if you can see that for element number 1, node 2 will be the far end. Okay, node 1 will be the near end. Okay, so we take the x at the far end, which is 3, minus, okay, x at the near end, which is 0. And the length of the element is 3. So you get 1 here. Okay, this is how you determine the Cx. And Cy will be sine theta, or using y at the far end minus y at the near end divided by the length. Okay, so we can see that y at the far end is 0 for element 1. Okay, and y at the near end is also 0. So you get 0 for C1. So once you have determined the Cx and Cy, you will need to determine Cy squared, Cx, Cy, so that you can put in the template. So you can get the Cx is equal to 1, Cx squared is equal to 1, Cy squared is equal to 0, Cx, Cy is equal to 0. Then how to put it in the template? Just refer to this template. If you can see that you are, the K11 is Cx squared. Okay, so you just get the Cx squared here and put into the template K11. Okay, then you follow with Cx, Cy, negative Cx squared and negative Cx, Cy for the row number 1, and you continue. Okay, so don't forget about this AE over L here. Okay, so you are going to put it this AE over 3, okay, for element number 1. Okay, so next, this number 3, you can, put into the matrix, then you become simplified in such. Okay, again, one more to be highlighted here is this numbering. 1, 2, 3, 4. Okay, you need to give a number to this matrix, okay, to indicate that this is the nx, this is the ny, this is the far x, and this is the far ny. Okay, so n is the mean, n means near n, f means far n. So x and y means the DOF direction. So meaning that you move, now we are still at element number 1. So if you refer to element number 1, okay, so we are going to name horizontal first, x. Okay, this is x direction. Okay, then the y direction, okay, vertical. So meaning that we move from near end to far end. So it will be 1, 2, 3, 4. So this is how the naming, okay, be done. So we'll need to continue with K2. Okay, here I will show you how to determine Cx and Cy again, okay, for this element 2. Okay, now this is node 1, this is node 3, and we have previously put the coordination 0, 0, and this is 3, 4. Okay, so therefore, to get the Cx for this case, we are going to look at just to put in the formula again. Okay, it will be x at the far end minus x as the near end divided by the L, length. Okay, y at the far end minus y at the near end divided by the L. Okay, so let's try. Okay. So for element number 2, x at the far end is 3. Okay, x at the near end is 0. Okay, 3 minus 0. And the length is 5 meters. Okay, you get 0.6 here. And then for cy, you have at the far end, the y is 4, and at the near end is 0. So divide by the length 5, you get 0.5. So you continue to get the cx squared, cy squared, cx, cy, and put it into the template. Okay, so if you can see that the 5 here, AE over 5, the 5 also need to put in the matrix. Okay, then we continue with the naming. Okay, how to name it? Again, it's from near end, x direction, and then y direction. Then move to far end, x direction, then y direction. So it will be at the near end, 1, 2, then go to the far end, 5, 6. Okay, this is how the numbering being done. Okay. So then the first question, okay, required, okay, for you to solve is to prepare a structure stiffness matrix. Therefore, you need to prepare the whole matrix. This will be the structure stiffness matrix. The size will be 6 times 6 because you have a total DOF for this structure is 6 number. Okay, so we need to determine this. But if the structure stiffness matrix is not requested, so we don't need to find all these elements. We just need to find the one that we're required to solve for the unknown displacement. Okay, so now how to determine the structure stiffness matrix? Maybe I will show you for K11 and K12. Okay, so we need to refer to the K1 and K2. So I might go back to the page, okay, to show you the. Okay, so let's say I'm looking at this K11, which also mean I'm referring to this column number 1 and also row number 1. So now I move back to the element number 1 and see whether I have row 1 and column 1. Okay, so I go. So now I have row number 1 and column number 1. So this one I have the value of 0.333. Okay, then I move to element number 2. Okay, so I also have this column number 1 and row number 1. So I have this 0.072. So you just need to sum up the 0.333 plus 0.072. So you will get this value. So remember the structure stiffness matrix is actually sum up all the member stiffness matrices. Okay. So probably we try another one. Okay, row 1 and column number 2 now. Okay, I will circle, okay, the numbers. Now let's look at this element number 1, column 1, row 1, column 2. Then I go to row 1, column 2. So the answer will be 0.096. Okay, so this is how you transfer all the information from K1 to K2. And then one thing to highlight here, okay, this is a symmetric matrix, okay, where the top part, okay, of the triangle is actually mirror, that can be mirrored down. Okay, so now let us look at this. Maybe I shall erase this. Let's say the structure stiffness matrix is not required in this problem. Okay, so we can see that okay, only the highlighted, I mean the regions, okay, these elements are needed, okay, to solve for D1 and D2. Okay, so let's see how it looks like. Okay, so it be something like this. Okay, so we can establish if your D1 and D2 you have two unknowns, means that you are going to have two simultaneous equations, okay, to be established. So the first one will be, you can put it out the AE. Okay, so it start with 0.405 multiply with D1 plus 0.096 multiplied D2. It should actually plus 0.333 multiplied 0, D3, and 0 multiplied 0, and so on, 0.072 negative multiplied 0, and plus negative 0.096 multiplied 0, and so on. But this D3 to D6 are all 0. Therefore, we can skip this process. Okay, so and then the other side of the equation should be equal to 0. Okay, then you form the equation number 1. Okay, so I will form equation number 2 right now. It will be 0.096 multiply D1 plus 0.128 multiply D2. Okay, remember the AE will be always here equal to negative 2. Then from these two simultaneous equations, you can solve for your D1 and D2. Okay, you need to understand D1 and D2, the meaning of D1 and D2. Okay, you will be always refer back to this DOF numbering. So 1 means the horizontal displacement for this node 1. Okay, and 2 will be the vertical displacement for the node 1. Okay, so that is why you should actually put D1 and D2 here. The unit is meter. Okay, so once you have solved for the displacement, okay, then you can continue to determine the support reaction if the problem asks for. Okay, so I will show you the region which is needed. So in solving the remaining Q3 to Q6 equations, you will require this region. Okay, so if you can see that Q3 will be equal to 0.333 multiply with, okay, right now you can see that this D1 and D2 has already found the value. Therefore, you can directly put in this equation. Okay, so meaning that AE can be cancelled out because it's not given to you just now, the value. So you can see that you get the negative 1.5. This negative 1.5 meaning that you need to refer to Q3. Where is Q3? Q3 is this horizontal reaction of this node 2. Okay, if it is negative, meaning that the direction will be opposite, okay, from what is shown here. Okay, so means that it goes to your left. Okay, so you can continue with forming the equation number 4, which is 0 multiply, yeah, then the whole thing will become 0. Okay, meaning that there is no forces acting at this direction. No, it will be equal to 0. Again, and it is very reasonable because if you see this joint, number 4 must be equal to 0 to make sure the equilibrium summation fx equal to 0. Okay, so you can continue with the Q5 and Q6 if requested. If not requested, you can skip this process. So that we can determine the internal force for member 1 and 2. Okay, I have to go back to my previous slides. Okay, we have discussed this in our previous class on this transformation matrix. Okay, at the end, if you want to determine the axial force for truss, we use this Q equal to K prime TD. Okay, this Q for this element, we will have Q at the far end and Q at the near end. Okay, and we can put in this, establish this equation by getting the K prime, okay, and the displacement transformation matrix, okay, multiply with the D. Okay, and if you look at this D, is a big D. Okay, capital letter D means the D that you have solved in your earlier equations. Okay, at the global. Okay, so but we need to know that QF is actually equal to negative QN, or QN equal to negative QF. Okay, because the axial force must be only one axial force in the element. Okay, therefore you just need to determine one. So it will be easier for you, okay, to take QF, because QF is tension. So once you get your answer is negative, you know that your axial force is in compression. Okay, so now we only extract this equation. Okay, QF only. So this will be the solely for QF. Okay, we can use this QF for determining the axial force for the truss member. Okay, so this will not be given to you. Okay, you need to know how to obtain from this equation. So now I'll move to our problem just now. Okay, so this is the equations that we are going to use to determine the axial force. Okay, for member one, we need to get, if you can see that we required length, Cx, Cy, and also the D. Okay, that we have solved. Earlier we have solved D1 and D2, which is this 4.5 and negative 19. Okay, therefore this is D1 and D2. Therefore, you need to put it here, okay? D1 and D2. Okay, then you need to go to member 1, okay, to find the Cx, Cy, and the information of the length. Okay, let's move back. Okay, if you can see that Cx is 1, Cy is 0, length is 3 meter. Okay, so, and then the numbering follows 1, 2, 3, 4. Okay, that is why when you come to this local, you name this D1, D value numbering based on your element 1. 1, 2, 3, 4. Okay, so you get the Cx, you get the Cy, you get the length, and then you determine, you solve for this equation. How to solve it? It will be negative 1 multiply 4.505 over AE, multiply with AE over 3, plus 0, multiply with this, and then multiply plus 1 multiply 0, plus 0 multiply 0, then you get negative 1.5 kilometer. And this negative means that this element is in compression. So for member 2, the naming is 1, 2, 5, 6. Okay, so let's move to, let's go back and see this element 2. So it is 1, 2, 5, 6. Okay, and then the Cx and Cy is 0.6 and 0.8, and length is 5 meter. So now if you can see that you are following whatever that you information from member 2 and the numbering of element 2. This is for the local, local. Okay, then put in the D1 and D2, D5, D6, okay, that you know, then you solve for it. Oops, this should be Q2. Okay, Q2. All right. So the example that I've shown you just now, okay, show the process of how to solve for unknown displacement, how to solve for unknown support reaction, and how to solve for the axial forces for the truss. Remember, in truss, we might have a condition where the truss is subjected to fabrication error and also temperature change. And this might significantly affect the results of the analysis. Therefore, we need to consider this also in the calculation. In this stiffness method, we are going to modify the equations, these stiffness equations. If you see that Q equal to KD is what we have used just now. Okay, in truss, we don't have Q naught that subjected to intermediate loading. Okay, but we will have a Q naught due to fabrication error and also temperature change. Okay, what you need to do is you need to just to plus Q naught. Let's say if the truss is subjected to fabrication error, the Q naught you need to plus with this equation. Okay, if you can see that we need AE, we need the delta L, and we need the information of L, CX, and also CY. Okay, so this delta L is subjected to these rules. If the member has fabricated too long, the delta L is positive. If it is fabricated too short, it is a negative. And then this equation, this template is not given to you, okay? And truss subjected to temperature change, okay? So global force displacement relations, okay? So we are going to add also similar like fabrication error, the Q naught, okay? But now with this equation, AE alpha delta T, and this CX CY, yeah, also we obtained from the member that's subjected to this temperature change. Okay, the delta T will subjected to these rules. If the temperature increase or the member has been heated, it has a positive value of the delta T. Oppositely, it will have negative value. Okay. So that is when you want to solve for your unknown displacement, you need to modify the stiffness equation. When you are determining the internal forces, you also need to modify the local stiffness equation, which you plus small q naught. Okay, for this small q naught, okay, when subjected to fabrication error, it is negative AE delta L over L. Okay, and for temperature change, it will be negative AE alpha delta T. Okay, so they you don't need to multiply CX CY like this. Okay, it will be just this value. Okay, but in the negative form. Okay, so let's try with this example. Okay, we're going to continue with the previous example, but now the member has some conditions. Let's say member 1 is fabricated 10 mm too short. Okay, and AE is given to you at with this value at 1000 kilonewton. Okay, so we are going to use this equation, fabrication error, and we need to determine the Q naught. Okay. So now only member 1 has this condition. Member 2, they are not subjected to fabrication error. So we are looking at element 1. Therefore, all these CX, CY, the L referring to element 1. Okay, and the numbering here referring to element 1. So it will be 1, 2, 3, 4. Okay, and the CX for element 1 is 1, CY is 0. Okay, we don't use the CX squared, CY squared, CX, CY in this equation. Okay, AE is given to you. Delta L is negative. Okay, 0.01 because fabricated too short, and the length given. So you need to determine this all the Q naught here. How to let's try for Q1 naught. Okay, it will be this 8000 multiply negative 0.01 divided by 3 multiply 1. Then you get the Q1 naught. Okay. So once you have obtained your Q naught, you need to put it back into this stiffness equation. Okay, I would say that you need to plus here Q naught. Okay, so you plus this Q naught. 1, 2, 3, 4, and 5, 6 is not, yeah, no value about that. So you need to, solve this, solve for the D1 and D2, as what I have explained earlier. Okay, so once you have solved for the D1 and D2, you can continue with solving support reaction if requested. Okay, here I will show you on what if you need to determine the internal forces. Okay, for member 1. Okay, remember, member 1 is subjected to fabrication error. So we need to add this equation. Okay, so this is the internal forces equation earlier, and we just modify it with the adding this fabrication error. Remember, it's negative. Okay, so it will be AE delta L negative 0.01 and the length 3. Okay, so and the D1, D2 you obtain from this solution here. Okay, so you can get back your Q1 if you can compare with the earlier problem. There is a very significant change, okay, of the value. Okay, so if you can see how to get this value, it is actually negative 1 multiply negative 0.00945. Okay, and then plus 0 multiply 0.00513 plus 1 multiply 0 plus 0 multiply 0, and then multiply with 8,000 divided by 3, and then only minus this value. So you get 51.87 kilometers. So you can try for the internal forces for member 2. However, member 2 is not subjected to fabrication error. So the equations will be up to this only. So you no need to add any consideration for fabrication error for member 2. Okay, so let's try for what if the member is subjected to temperature change. Okay, so now is the member 2 that have this condition. Okay, so given the alpha, okay, 11.7 pound negative 6, and then A is given to you. Okay, so this is the formula, okay, to get the Q naught, okay, due to this temperature change. So 1, 2, 5, 6 is for member 2 numbering, okay, and the CX, CY you can take from the earlier example from member number 2. Okay, so you have to fill in the template, and then we have AE is 8,000, alpha is 11.7 power negative 6, and delta T is 80 degrees Celsius. Then you can solve for your Q naught. Again, you put in the Q naught into the stiffness equation, you solve for the D1 and D2. And using this new D1 and D2, okay, you can solve for your internal force. Okay, if you can see that in this case, okay, so member 1 do not subject to any temperature change. Therefore, we no need to add any this modification to these equations, okay, for the internal force. No need to add, okay. But for member 2, yes, you need to add this AE alpha delta T, okay. So this is how, yeah, this is how the, the analysis done, okay, for the truss that's subjected to temperature change and also fabrication error. So I will stop recording this lesson.